So basic integration by substitution, that's quite nice. We're looking for nice simple ways to substitute in for parts of expressions to make them easier to work with and integrate. However, sometimes they're not always that straightforward, and there's a few special cases we have to bear in mind, and that's what we're going to cover in this video. However, what we have to be able to do is remember several trig identities, because we have to be able to work with them throughout our time here. And that's this list here. So we need to remember sine squared a plus cos squared a is 1. We need to remember that sine 2a is equal to 2 sine a cos a. We need to remember that cos 2a is equal to cos squared a minus sine squared a. And that can be then written in the format of 2 cos squared a minus 1, or 1 minus 2 sine squared a. And we also need to remember that tan squared a plus 1 is equal to sec squared a. So these here should be standard formulae that we remember from higher. Go back and have a look at them if you don't. We also need to remember trig relationships relating to the functions themselves. So for example, tan a is sine over cos, cot a is 1 over tan a, sec a is 1 over cos a, and cosec a is 1 over sine a. These are all standard trig forms and relationships that we need to remember. These will all come into play when we're doing our work, and these are all things we have to be able to identify and work with throughout. Now there's a couple of different formats that I'm going to look at here in terms of special equations and substitutions that we need to be able to do. The first one is when we look at it and we have an integral of the form integral of square root of a squared minus x squared dx. Now if you see one of this format, try using a substitution x equals a sine u. Or we can equate that as u equals sine minus 1 of x over a. What this does is this takes it and writes it in a format such that we can then do a bit of factorising and write it as a simple trig function, which can then be a lot easier to integrate than working with what we've got there. So if we look at the example I've got here, I want to find the integral of square root of 3 minus x squared dx. Now for this one here, if I think of it as being a squared minus x squared, I'm able to say that a squared is equal to 3, so I know that a is equal to the square root of 3. If I then go back to think to myself, right, this is a standard form that I'm going to use for my substitution, let's see what happens. What that then lets me do is say, fine, so what I'm going to do is I'm going to use x equals the square root of 3 sine u. And I'm going to substitute it into here to see what I get. So if I substitute this into here, I'll end up with the integral of the square root of 3 take away square root of 3 sine u all squared. So that'll then end up giving me 3 sine squared u. But I also have to get rid of this dx. To get rid of the dx, what I'm going to do is take the derivative of all of this. So what I'm going to say is dx by du is equal to the square root of 3 times cos u, because I know that's the derivative. So I can rewrite it as dx equals root 3 cos u du. What I can now do is substitute this in for the dx. So that's then going to be times square root of 3 cos u du. Now if I focus on the square root here, what I can do is take out 3 as a common factor, and I'll end up with the square root of 3 bracket 1 minus sine squared u. Now if you think back to the trig identities we had before, I know that cos squared plus sine squared is equal to 1, so I can rewrite that and say that cos squared equals 1 minus sine squared. So what that then allows me to do is rewrite it as root 3 cos squared u. And if I then have it rewritten like this and separate both parts, what I can then rewrite that as is root 3 cos u. So I can then take this and substitute it back in for this bracket section here and say fine, so what that then gives me is root 3 cos u times root 3 cos u du. So what I can then get is the integral of 3 cos squared u du. So now that I've got that, what I can then do is integrate it. But we don't like integrating cos squared functions. So what I have to do is then substitute in for cos squared u. If I substitute in for cos squared u, I substitute in a half, bracket 1 plus cos 2u. For that, my integral then becomes 3 over 2, which is going to take the constants out, bracket 1 plus cos 2u. And that's du. Now I can integrate this easier. We don't like integrating to the powers if there is not another trig function part here. I'll show you how we do one with powers in a few minutes, but we don't like it if there's not one here that would involve, for example, a sine u. So I end up with 3 over 2 times the integral of 1 plus cos 2u du. If I integrate that, what I end up getting is 3 over 2 bracket u is then integral of cos 2u, so that's plus a half sine 2u all plus c. So what I now have to do is eliminate the u such that I can then get this into a nice simple format for me to use. So if I go back to it, let me just rewrite it out. I've got 3 over 2 bracket u plus a half sine 2u plus c. If I think back to some other trig identities I've got, again think back to the list I gave you, I know that sine 2u is equal to 2 sine u cos u. And if I then substitute that into here, I can rewrite that as 3 over 2 bracket u plus, well, a half times this plus sine u cos u. And that's plus c. Now if we think back to our original substitution, what we chose was that x equals root 3 sine u. What I can do is rewrite this as u equals sine minus 1 of x over root 3. Now, I have an expression there involving sine. What I don't have, though, is something involving cos. What I have to do is rewrite this cos in terms of sine using the previous identities we had. And I'd have it written as 3 over 2 bracket u plus sine u times the square root of 1 minus sine squared u plus c. Looks a lot more complex than it is, I promise, but if we write it in that format there, what we have is it all written in terms of sine, so we can then take that and figure it out from there. If I take this here and rewrite it as sine u equals x over root 3, I now have something that I can substitute in for the sine u's. What I can then do is substitute that in for the sine u's, but I've written u equals sine minus 1 of x over root 3, and you're saying, why have you gone from that to that? I have a u here as well. So I've got something to substitute in for that u. So what I can then do is say, therefore, let's call it I, my integral. That's going to equal 3 over 2 bracket sine minus 1 of x over root 3 plus, well, sine u is x over root 3 times the square root of 1 minus sine squared u, if sine u is that, sine squared is x squared over 3. Close bracket. I've then got a plus c. So what I can now do is do a bit of algebraic jiggery-pokery with that, and if you do that, so take out the 3 here, in front of there is a square root of 3, work through and factorise this part here, what you'll end up getting is a final answer where I equals a half bracket 3 sine minus 1 of x over root 3 plus x times the square root of 3 minus x squared, close brackets, plus c. Now if I hadn't taken the 3 from here into the bracket, I'd have ended up with 3 over 2 here. I wouldn't have ended up with 3 in front of this, and I'd have ended up with an x over 3. So again, that would be the equivalent answer. We've just tried to neaten it up a little bit. Now that's a lot of work for a few marks, but we have to remember if it's of that format, this actually, despite your thinking, does make it a heck of a lot easier to work with and integrate than playing about with it in a different manner. Big reason being we've no derivative on the top. So we can't use our integration where we've got a derivative on the top and have a function on the bottom and substituting that way. Another standard integral is if we have something of the format integral of 1 over a squared plus x squared dx. For this sort of one, we try using x equals a tan u. If we have it written like that, we can rejig this about and have u equals tan minus 1 of x over a, which can then be used as part of our equation later. So let's imagine I want to find the integral of 1 over 3 plus x squared dx. If I'm going to do that, what I'm going to do is start by letting x equal square root of 3 times tan u, following the format we've got here. If I have that, what I can then do is substitute it into here. So I'd then be able to say I've got I, the integral, is equal to the integral. My bottom would become a squared, so that would just be my 3, plus all of this squared here, so plus 3 times tan squared u. Now, the top has the dx on it, so we have to get rid of that somehow. And to get rid of that, we take the derivative dx of this. Now the derivative of the square root of 3 tan u would give me square root of 3 sec squared u du. So I can use this to get rid of the dx there. Substitute that in on the top, and I end up getting root 3 sec squared u du. So it doesn't look any simpler. However, if we've got this on the bottom, 3 plus 3 tan squared u, what I can do is take it a 3 as a common factor and have 3 bracket 1 plus tan squared u. And again, think back to the identities. 1 plus tan squared is sec squared. So I then end up getting 3 sec squared u. So I can take that and then substitute it back into the original equation. I'll then end up with the integral of root 3 sec u over 3 sec u du. Now that is actually really nice because that simplifies, cancelling out, as the integral of 1 over root 3 du. Simplest style of integration, we're integrating a constant. So integral of 1 over root 3 du, that gives me 1 over root 3 times u plus a c. Now again, we go back to the original part here. We know that if we've got an x in this format, we get a u in this format. So if I've got x equals root 3 tan u, I can rearrange that and get that u is equal to tan minus 1 of x over root 3, which can then be substituted in here to get rid of the u. And if I do that, what I'll end up getting is 1 over root 3 tan minus 1 of x over root 3 plus c. So there you go, there's my final solution for that. So they don't look the simplest, however, they actually do become a lot easier once we remember these standard substitutions that we have to be able to use. If we use them every time, we'll actually break them down and make it a lot easier than we want to be.